Hello everyone, welcome back again to this online structural geology NPTEL course. We are learning deformation mechanism this week, and we are part 4 of this lecture series. And today we learn in this class diffusive mass transfer. In part 1 we learned crystal defects, in part 2 we learned cataclastic deformation, part 3 went on intracrystalline plasticity, and this one is the last one where we learn diffusive mass transfer or diffusion creep. So, we will mostly cover in this lecture some sort of processes, different processes of diffusion assisted deformation. Then we will classify it and then see some general overviews on diffusion and their governing equations. And then we also see the relationships between strain rate, stress, and if there are some other parameters related to the flow laws in the diffusion creep regime. So, these three are the major areas that we will cover in this lecture. So, first of all, let us classify, as geologists or any science always does, that classify the processes. So, diffusion creep mechanisms are generally classified in 3 different classes. So, the first one is diffusion precipitation creep or DPC. This is diffusion of dissolved matters through fluid. When that happens, then it is dissolution precipitation creep. Then diffusion of atoms or vacancies through grains. When that happens, then we call it Nabarro herring creep. And if the diffusion of atoms or vacancies do happen along the grain boundaries, then this is known as Coble creep. So, we will take over one after another. First, we will look at dissolution precipitation creep, then Nabarro herring creep, and then the Coble creep. So, dissolution precipitation creep is essentially a creep or diffusive mass transfer by the assistance of any fluid. So, it can happen in a short distance, so from one side of the grain to another side, or it can happen to a very long distance like stylolites and some vein filling processes. So, here there are 2 examples. You can see that these 2 are 2 fossils. So, this one is a petrified wood, as you can see in this first image, and we know that the initial composition of any tree trunk is carbon. But in a petrified wood, it is either replaced by silica or carbonates, and mostly silica. It is replaced by silica, and therefore, the entire thing get transferred to silica, and that happens atom by atom diffusion processes with the assistance of some sort of fluid. And the same one is here. We have seen this animal before. This is a trilobite. It is not a carbon anymore. So, each and every cells of this animal, each and every atoms of this animal are replaced by silicate materials. And what we see in the middle, this is a thin section of a shell, where you see that this shell has some sort of foliations, and these 2 things are the veins or the fractures that later, so fractured opened and then later got filled by some calcite rich or carbonate rich fluid, and then these fluids sort of diffused from this matrix and slowly filled in the open space. So, these are the processes, some sort of mass transfer through in assistance of some sort of fluids. Now, diffusion controlled dislocation precipitation creep is important in very fine grained rocks, and the rock has to be wet, and mostly rocks with where you have the minerals or in its compositions which are soluble in water or carbon dioxide. Fundamentals of dissolution precipitation creep. Now, there are some ideas that we can think of. So, dissolution can happen at a point and dissolution can happen on a surface. So, whatever happens when the 2 points touch each other or 2 surfaces touch each other, then a pressure is generated on the surface, and if there are some fluids, then the process is known as pressure induced dissolution or pressure dissolution. So, pressure dissolution is a process where the minerals dissolve as the result of pressure applied externally to them, and this may happen because minerals under pressure and thus some sort of undergoing elastic or temporary strain are more soluble than unstressed minerals. So, that means if you have a mineral under stress that has better solubility than a mineral which is not under stress, and because you have some sort of fluid which is helping the minerals to get dissolved, it is also known as chemical compaction. So, here are these 4 images A, B, C and D, these 4 illustrations that tells you. So, you can imagine that these white areas are some sort of sand grains, and then they touch each other slowly. This the force is generated on this side, and then they dissolve here at the surface, and finally this becomes like a sutured boundary or sutured contact between these grains. So, when this happens, certainly some materials got dissolved here and they get deposited on the sides of this grain. So, this is the some what you see. So, these are some microstructures of resulted from dissolution precipitation creep. What do we see here? That this is certainly a grain, you can see under microscope that people have snapped, and then this part you can see that it had a contact with this grain in this side and also in this side. So, this part of this grain got dissolved, and then dissolved material got deposited in this region. This is known as overgrowth of quartz. Now, I just wiped it out. So, now you can see it very clearly that this is your grain boundary, and the grain has overgrown due to the precipitation of the dissolved material from this side. You can also see in the second example here in this image, this is where the dissolution had happened, and then this was the original grain boundary, and this is the overgrowth of this quartz. So, if you see this kind of microstructures, nail it that this has happened due to dissolution precipitation creep. Now, if it happens on the surface, so initially we develop some sort of a plane which is known as dissolution seam. So, you have one grain here or one area here, and then you have another area here, they just compress each other, and then a dissolution seam along which the materials get dissolved, you form this dissolution seam. And sometimes when you go with higher pressure, then this seam tries to slip along this line, and then it develops a structure, we call it stylolite, and if it can happen in a very dense way. So, this we call highly serrated stylolite, and this stylolite can also get deformed, and then we call it deformed stylolite. So, in 3 dimension you can see the stylolites, they look like this. In the previous image, in the previous slide, you may have seen that these parts are little thicker compared to this part, and these parts are thicker because you always have some materials which do not get dissolved in the fluid. So, they stay here as a residue, and if we try to look at in 3 dimension, this is how it looks like in a 3 dimensional block. So, you see these are the columns of the stylolite, and here in this area you have this insoluble residue, they stay like that. And of course, if you see it from the side, then these are your places where you have some sort of relative displacements of the initial dissolution seam. So, this is how the stylolites do form through the process of dissolution precipitation creep. Now, here there are some examples in this image. So, the first one, you can clearly see that something has happened along this, and if you can match the illustration of one of the previous slides, this is essentially, or you can nail it as a dissolution seam or initiation of stylolite. You can also see here some sort of dissolved seam here, and if that happens in a regular manner, in a regular arrangement, then it also develops some sort of layers in the structure or repetitive layers in the structure. So, therefore, you can also call it a cleavage or foliation. So, this is the mechanism, or this is the process how you see dissolution precipitation creep, and this is how they look like under microscope. Now, I have 5 images which I collected from different web pages or different papers, and I leave these 5 images for you to interpret which one is dissolution seam, which one is stylolite, which one is highly serrated stylolite, and which one is deformed stylolite. So, you can look at these images in detail, go back to the previous slides, check them and match them and identify by yourselves which one is what. Now, if we try to theorize this dissolution precipitation creep, it is important to understand that the solution or the fluid you have in your system must have a concentration less than the concentration has to be less, so that the materials can dissolve within this, and if the concentration is high, then the material would not dissolve into it further, rather it would precipitate. So, there must be some sort of an equilibrium concentration. So, we can think that all minerals can dissolve in fluids, it can be dissolved in water, it can be dissolved on carbon dioxide or so on, and therefore, as we talked about, there is an equilibrium concentration. Let us assign these as CEQ. If the actual concentration is lower than this equilibrium concentration CEQ, then the minerals do dissolve, and then the concentration of this fluid increases towards the equilibrium concentration. This is very simple, because if you are adding more materials to the solution, it would slowly try to saturate and achieve the equilibrium concentration. If otherwise, that means the actual concentration is higher than the equilibrium concentration, then the minerals would precipitate and the concentration would decrease towards equilibrium concentration. So, that means if I have this curve, this line as CEQ, then does not matter where I am, it would always approach towards the equilibrium concentration. If this is, so this is high and this is low. So, if this is low concentration, that means here then it would dissolve more material and try to achieve the equilibrium concentration. If in this side that it is oversaturated, then it would precipitate materials and it would try to achieve the equilibrium concentration as well. So, some equations, these are very simple, do not worry about it. So, the chemical potential, if we consider it as phi, is a function of pressure. So, we can write this equation, and then concentration is also proportional to, is a function of this chemical potential or phi, and this is proportional. So, we can write it this, and then by replacing these two equations we can come out with this equation C equal to sigma p, where sigma here and here is a constant. So, at equilibrium concentration, therefore, we can come out with this equation, which is a function of pressure, a constant, and an initial concentration or threshold concentration, which is C0, and this is your equilibrium concentration. This equation is important, and we will come back to this soon. So, if we have to derive the flow law, we are not going to derive it, we will state it, but I am trying to give you some sort of ideas that how these are being derived. So, the functions that we need to take care of, or parameters we need to take care of, are equilibrium concentration, pressure, chemical potential, and so on. And we have seen that equilibrium concentration is a function of pressure, and if there are some sort of pressure gradients, then you also generate concentration gradient, and you also generate diffusion transport of matter. And if you diffuse material, or if you move material from one end to another end, you change the shape of the material, the block, and therefore you generate strain. What I mean by that, if I have a shape or a crystal like this, and then I dissolve materials from here and here, these materials get dissolved, and if they are being deposited here and here, and if I remove this part, so actually achieve something like this. So, clearly my initial shape was something like that. So, this part, so I certainly have achieved some sort of strain in the crystal. So, this is how it happens, and then to derive the flow law, you need to know what is the pressure gradient and what is its relation to the differential stress. And it happens in 3 different stages, which are in sequence. First, you have to have a dissolution reaction, that means you have to dissolve your material, then you have to transport it through the mechanism of diffusion, either, and in this case mostly along the grain boundaries or through an open space, and then it has to precipitate somewhere. So, first one is dissolution reaction, then transport through diffusion through grain boundary fluid, and precipitation. The flow law is given in this form: strain rate is equal to a constant A d c multiplied by diffusion coefficient delta sigma stress, and this part is very important. G is the grain size, or sort of a length of the grain, which is cubed. Now, this tells you very clearly, first thing we need to observe, that what is the relation between strain rate and stress. If we see this equation, strain rate is proportional to stress. So, this is linear. So, the flow is Newtonian, we can clearly see from the equation. And what is important, that strain rate is inversely proportional to grain size, and that even to the power of cube. So, that means it is extremely grain size sensitive. That means lower the grain size, faster the dissolution precipitation creep would happen. Or these two are the take home messages from this equation, that this is a Newtonian flow, that means the strain rate is linearly proportional to the stress, and it is extremely grain size sensitive mechanism, where lowering the grain size would make the deformation faster. Here we try to see what are the role of pressure and then chemical concentration in activating the dissolution precipitation creep. Now, what we see here, if we consider that this cube is a grain, where one arm of this grain has a length of g, and if I apply some force here on this surface, this surface, this stress, which is a positive stress, compressive stress, and then therefore, on the other side we have a negative stress, a tensile stress on this side. So, this surface is under compression and this surface is under tension. Now, under differential stress, at least in this condition, the grain boundaries have different effective pressure. So, if I have my initial pressure P, which is a confinement of this grain, you can imagine, then on this surface you have initial pressure plus this one, and on this surface, on this tensile surface, you have P initial pressure minus this one. And if we have to find a mean stress in this illustration, which is this one, then clearly at this surface we have stress level somewhere here, and on this surface, on this tensile surface, we have stress level somewhere here. So, if we now can imagine that with time this would try to dissolve the material here and which would be precipitating on this side. So, therefore, the compressional side would dissolve and it would add on the extensional surface. So, this drives the transport from compressional grain boundaries to the extensional grain boundaries. And if we try to look at in terms of equilibrium concentration, and we can think of in a very similar way that we have this side applying some stress and this side we have the tensile domain. So, this is compressive domain, this is tensile domain. So, perpendicular to this one we have a very similar equation we have derived. So, here it is plus and here it is minus. So, here it will be less, and therefore, again we would have higher equilibrium concentration at the compression surface and lower equilibrium concentration at the extensional surface, and this would also drive your transport from compressional grain boundaries to extensional grain boundaries. That means, materials would move from this side to this side. Now, if I try to combine both, then things would move from this side. So, if I look only on this surface, I clearly can see that this was the square, this G, and then this side is getting dissolved and is being precipitated here. So, I am just showing it in one way. So, eventually you are getting something which is greater than G, say G prime. So, clearly G prime is greater than G, and therefore, you achieve some sort of strain, and slowly you also approach the equilibrium concentration from this part to this part. So, diffusion then tries to equalize the concentration. If that happens, then you are doing the transport. Compressional phases are under saturated most of the cases. So, therefore, you would have dissolution. So, material will dissolve on compressional surfaces, and extensional phases are oversaturated. Therefore, you would have precipitation on this surface. So, these are the three basic mechanisms. First, you have dissolution, then you have transport, and then finally, you have precipitation. Now, let us have a look on the other two processes, that is Nabarro-Herring creep and Coble creep. But before going into the details of this, we will have some basics of this diffusion induced creep. So, during this type of creeps where the atoms move from one side to another side of these grains, the atoms migrate, or they can migrate, they have options to migrate either through the crystals or along the grain boundaries, from again areas of high compressive stress to areas of low compressive stress. And therefore, when the atoms move from one end to other end, the vacancies also move from the other end to one end in the opposite side. You have learnt it when you have learnt the crystal defects. So, the mechanisms by which the vacancies and at the same time the atoms migrate is known as diffusion. Now, the directed diffusion of atoms under stress, that means all the atoms, if they are moving to a particular directions and the vacancies to the opposite directions, then this can lead to the change of the shape of the crystal where the volume remains constant. And characteristically, this diffusion creeps, this Nabarro-Herring creep and Coble creep, they do operate where the stress levels are very, very low, and also grain size is extremely smaller, and this we generally get at lower mantle or below of the earth. And we will see why the grain size should be smaller, and even between these two processes we need the grain size sensitivity is also different in Nabarro-Herring creep and Coble creep. Now, transport of the vacancies, we know that it happens, the vacancies exchanges places with the neighboring atom, we learnt about it, and when one vacancy jumps to a neighboring site, the volume does not change, the density remains constant. So, one atom replaces the vacancy, resulting to the change of the shape, and therefore, we achieve the deformation. We talked about it many times. The direction of vacancy transport is opposite to the direction of the material transport, this we also have learnt. And here Fick's law is somehow important, where flux is directly proportional to the distance and indirectly proportional to the chemical concentration of the fluid or the material we are talking about. Now, we will have a look of the two different processes that we have learnt, one is Nabarro-Herring creep and another is Coble creep. As we have classified in Nabarro-Herring creep, flux of vacancies do happen through the grains, and that leads to the deformation. So, you can see here this is a grain with this yellow atoms inside, and outside there are some white vacancies. Now, in Nabarro-Herring creep, the flux happens through the grain, so inside the grain. So, these vacancies would move through the grain to here, and they will appear somewhere here, and they displace these 5 atoms, they come here. So, therefore, the shape actually change from this to this, and therefore, you achieve a deformation, you strain the material, you change the shape of it. Here is a somehow the same example we have shown with 3 grains. So, this is how the atoms are moving from here to here, vacancies on the opposite side, and therefore, you continuously strain the grain, and you can see that here, if I consider this is the initial distance, then here the final distance or final height. So, it essentially got shortened, and on the other side it also got extended. So, elongation on this side and shortening on the other side happened through the process of Nabarro-Herring creep, where the fluxes happened through the crystal. Now, in Coble creep, instead of moving these atoms or vacancies through the crystals, they move along the boundary of the grain, and does not matter how they are moving, but we more or less can achieve the similar shape, but the mechanisms are different. Again, this is the size of the grain, you can think of with the yellow atoms inside and the vacancies outside, and these grains, or I am sorry, this grain particularly take the shape of this in a very similar way. And here, instead of moving through inside the grain, the movements do happen along the grain boundaries, but the result is very similar. Now, it is interesting to note that the flow laws of Nabarro-Herring creep and Coble creep, they look very, very similar. So, for Nabarro-Herring creep, it is exactly like this, and for Coble creep, it is like this. What we see here, that both of them are Newtonian flow, the strain rate is proportional to stress. Both of them are grain size sensitive. In Nabor-Haring creep it is squared, and in cobalt creep it is cubed. Here in these equations, so the d is the grain size. So in the previous slides, g has defined, or g was assigned as grain size, but in this slides I have defined as d. I should correct it, but now you know that d means grain size here. Now why it is so that one is, so clearly this is less grain size sensitive than this one. So you know that in cobalt creep it has to move along the grain boundaries. So shorter the grain size, faster is the process, but if it is happening within the grains, then it has to pass through the grain. So it is not that grain size sensitive compared to the cobalt creep. Therefore in the equation it is cubed and it is squared, and as we have learned that both of them are temperature sensitive, and generally it happens at very high temperature. So the microstructures of diffusion creep, it's not so easy to identify under optical microscopes, but when the diffusion creep is active, stresses are too low to move the dislocations. This is why it happens. There is no major driving force for dynamic crystallization. So therefore you do not achieve some sort of grain boundary migrations or so on. Therefore you have to have the diffusion creep. Now only force for recrystallization you have is the surface force, and therefore it develops a very strong shape preferred orientation. So you do not have any dynamic recrystallization, that means that there was no deformation or there is no thermal overprint. And also very interestingly, because diffusion creep is essentially movement of the atoms, so it is used heavily by petrologists and metamorphic petrologists for mapping the movement of major and trace elements, and this also gives you an idea of the pressure and temperature of the deformation and metamorphism as well. So if we think of the application of diffusion creep, there are many, but I will give you one. As I talked about that you can use it for mapping the movement of major or trace elements. So the zoned minerals in particularly that we see in nature very frequently, with different patterns of chemical profiles for different elements, sometimes are used to infer the orogenic pressure temperature conditions, and most of the times fluid histories. And garnets in particular is one of the candidates for such studies. So what happens here, the diffusions of particularly divalent cations, for example magnesium, manganese, calcium and so on, in metamorphic garnet is negligible at low medium grade. So if I have some distribution of these elements inside the garnet at low or medium grade metamorphism, then they stay there. So therefore if I have a large garnet crystal, the core of this garnet is almost undisturbed, it is some sort of isolated from the surroundings. But if the temperature is high, then diffusion starts operating, and then the elements, particularly the divalent cations, they move within the garnet following a typical pattern. What has been shown by several studies that garnets with prograde growth zoning tend to have manganese or calcium rich cores, with manganese number increasing steadily towards the rim. So volume diffusion becomes very fast process at high grade for originally zoned garnets to become compositionally some sort of homogeneous. So you have initially a very heterogeneous rimmed or zoned garnet in terms of a particular element, but when you have high temperature, then the volume diffusion starts of these elements and then the entire garnet becomes homogeneous in terms of the distribution of these elements. So, here is an example, as you can see here, the 3 different garnet grains mapped with microprobe or EPMA, the different elements. I have here only shown the manganese. The warmer color, the red colors, means you have higher concentration, and colder colors, blue, that indicates you have lower concentration. So, in this cordierite zone, the first one, the temperature was estimated 425 degree centigrades and pressure 3.5 kilobars. Here you see that manganese has higher concentration at the core and it is slowly decreasing towards the rim. When temperature is elevated and pressure as well to 535 degree centigrades and 6 kilobars in the garnet zone, you see that these manganese elements are diffusing towards the rim, and even at higher temperature and pressure at staurolite kyanite zone, you see that this manganese are more or less homogeneously distributed, and even their concentration somehow has increased at the rim, and also this is the rim and also at the inclusion boundaries. So, this is how the diffusion do happen. This process is extremely slow. So, geologists or particularly metamorphic petrologists do use it for calculating different types of geobarometry and geothermometry. So, we are done with this lecture of deformation mechanism. The entire week might be a little long for you with this lecture time in particular, but it is important that we now interestingly have developed a solid background on the theoretical aspect of structural geology. We have learnt strain in detail, we have learnt stress in detail, we have learnt rheology, and now we are done with the deformation mechanism. So, from now on we will use all this knowledge of strain, stress, rheology, deformation mechanism and so on to understand and interpret the different geological structures that we commonly see in the field. And we will start in the next week with planar and linear structure. So, thank you very much. I will see you in the next week.